This homework assignment begins with a tutorial question. I'm going to skip that for the purposes of this video because it gives full explanation as to how to do the calculation. So I'm moving on to the second question in the assignment, which talks about the acceleration due to gravity on Saturn. Here at the surface of the Earth, the acceleration due to gravity is about 9.8 meters per second squared. And so that's only at the surface of the Earth. Everywhere else you go in the universe, you have to calculate what is the value of G. So you might become curious, what is the value of G on the surface of other heavenly bodies? For example, on the surface of the Moon, the value of G is 1/6 of what it is on the surface of the Earth. On the surface of Mars, it's about 1/3. On the surface of Jupiter, it's 12 times. This question's asking, what is the acceleration due to gravity on the surface of Saturn? So what you need to do this calculation is, well, first of all, you need to know that the acceleration due to gravity is the universal gravitational constant, the mass of the planet divided by the distance to the center of the planet squared. So in the case of this calculation, I'll be doing universal gravitational constant, which is 6.67 times 10 to the minus 11th, the mass of Saturn, which is given in the problem, and the radius of Saturn, because the distance between the center of Saturn and the surface of Saturn is the radius of Saturn, and that's squared. So you just have to put those numbers in and calculate them, but you get a very curious result. I mentioned, and we all know, that the acceleration due to gravity on the surface of the Earth is 9.8 meters per second squared. When you do this calculation, you get a result that's even only slightly higher, despite the fact that Saturn has a mass that's 100 times greater than the mass of the Earth. You think, heavier planet, more gravity, right? Well, of course, Saturn is much, much larger than the Earth. In fact, it's 10 times in diameter, 10 times in radius. So when I look at this equation, if I look at the numerator, and I would increase the numerator by a factor of 100, because the mass of Saturn is 100 times the mass of the Earth. In the denominator, putting in the radius of Saturn is a number 10 times larger than the radius of the Earth, but of course that's squared in the calculation. 10 squared is 100. So when you do this calculation for Saturn, sure, the mass is greater by a factor of 100, but so is the radius squared greater by a factor of 100. A way of thinking of this is realizing that in order to calculate the volume of a planet like Saturn, you would use the volume equal to 4/3 pi r cubed. And so the density of Saturn, which is the mass divided by the volume, is much, much lower. So because Saturn is a low density planet, the acceleration due to gravity on the surface of Saturn is not as big as you might expect based on its very, very large mass. This next problem involves a classic experiment. Once Isaac Newton realized that the universal gravitational force law was the product of the masses and inversely proportional to the square of the distance, that had to be experimentally verified by measuring an amount of gravitational force, which is very, very tricky to do because the gravitational force between everyday objects is in fact quite small. Here in this problem, we're given two lead balls. They have different masses. We'll call them M1 and M2. And we want to calculate how much gravitational force there is between them. And that's relatively easy to do because we take the universal gravitational constant, 6.61 times 10 to the minus 11th, multiply the two masses and divide by the distance between their centers squared. All that information is given, so calculating the force is quite easy. A little bit of an important step is to realize everything has to be meters, kilograms, and seconds. So I'll have to convert the distance between the spheres, which is given in centimeters, into meters. And their masses are given in grams, which I'll convert to kilograms to calculate this force. And when I do, I discover it is a spectacularly small force. And so it's very, very difficult to measure experimentally. The problem goes on to ask you to compare this to the weight of one of the balls near the surface of the Earth. That is, take the mass of it. I think in my example it was 150 grams, which is 0.15 kilograms. The weight of that is just 0.15 kilograms times 9.8 meters per second squared, as we do near the surface of the Earth. So just divide those two numbers to get the ratio. The obvious lesson there being that the force between two everyday objects is very, very small indeed compared to the weight of the objects themselves near the surface of the Earth. This problem is a fairly tricky one because of how it deals with the ratios of masses and radii when it comes to gravitational force. You're told the gravitational force of a star on an orbiting planet 1 is F1. Planet 2, 3 times as massive as planet 1 and orbits twice the distance from the star, experiences a gravitational force F2. You want to know the ratio of the forces F2 to F1. So what I'm going to do here is explicitly I'm going to divide the two equations. Here, F2 equals G, M2 times the mass of the star that is being orbited, divided by the radius of the orbit squared. So that's G M2M over R2 squared. I'm going to divide that. Yeah, that's a fraction I made out of two equations. I'm going to divide that by the force on the first planet, F1, is equal to G M1, the same star, because each one of these planets orbiting the same star with a mass capital M, divided by the radius of planet 1's orbit R1 squared. Now, when I take this fraction of the two equations, you'll notice immediately that when I divide F2 by F1, the capital G's cancel. Universal gravitational constant is in both. And the mass of the star that is being orbited also cancels in this equation. What I'm left with is that F2 divided by F1 is M2 divided by M1, because I have an M2 in the numerator and M1 in the denominator, and R1 squared divided by R2 squared. Notice that it flipped, but that makes sense because the R1 and the R2 are in the denominator of each of the equations. So then I have to work out, what does this mean for the question? What the ratio of the forces? Because I don't know the masses and I don't know the radii, but I do know that M2 is 3 times M1. Imagine I substitute into this algebra where it says M2, I'll put 3M1. The M1s then cancel, and I have a factor of 3. I'm also told that R2 is 4 times R1, which means it's 1/4 R1. I'm sorry, that the force would be 1/4 what it is on R1. So I get a factor of 3 from the masses, and I get a factor of 4 in the denominator from the ratio of the square of the radii. So in the case of my numbers here, the ratio of F2 to F1 is 3/4.